before we continue to classify matter, I suppose we should define what matter is, right? Often people hear a definition for matter as anything that has mass and takes up space. I'm cool with that. The whole taking up space part, that's a measure of its volume. So if matter is anything that has mass and volume, it should be measurable mass and volume. So obviously things like fire is always one that comes up. Fire is probably not matter. It's a form of energy. You can't take the mass of fire and you can't measure its volume. It's not measurable. Feelings are not matter. You cannot take the mass of anger. You cannot take the volume of excitement. Not matter. Not that you thought that they were to begin with. From there, we're going to define matter as either being a pure substance or a mixture. In a pure substance, all the particles are the same. Now here's what could be a little tricky. All particles are the same. Those particles could be single atoms. Okay, it could be made up of single atoms, which might look something like this. So maybe I have a beaker, and my beaker is filled with, I don't know, iron metal. So I've got these individual atoms, and they're all the same. The symbol for iron is Fe, so make little Fe's. Now obviously these are gigantic atoms, but you get the picture. That's what I'm picturing in my head. This would be a sample of iron. Iron metal. Pure substance. All of the particles are the same. Little atoms of Fe, iron. People usually get that one right. Here's the one that they get a little bit stuck on. What if I have a beaker of water? What if I have a beaker of water? Okay, so here's my water. And in a previous video, we were looking at water molecules. Water molecules had a big oxygen and two little hydrogen. H2O. So we'll get a couple water molecules drawn. So I'd say this is water. H2O. And this iron was symbol Fe. And here's my water molecules. Okay, so now here's the deal. That beaker of water is still a pure substance. Every particle is the same. Every particle in that beaker is H2O. They're all the same molecule. A pure substance has to have all particles the same. The particles have two options. The particles could be individual atoms, like the Fe iron. It's just little iron atoms, and they're all the same. Or the particle could be a molecule. A molecule is when I have groups of atoms chemically bonded together. But as long as every molecule is the same, that's still considered a pure substance. Every molecule is the same. They're all H2O. Yes, it's still pure. Here's where people will get confused. Let's say they look at a beaker of water in the lab. They'll say, oh yeah, that's a pure substance. There's nothing else in there. It's water. But then they look at the picture and they say, no, that's not pure because there's different kinds of atoms. You've got oxygen atoms and hydrogen atoms. They're different. Then they'll say, nope, that beaker of water, that's not pure. But wait a second. When you looked at it in the lab, you just said, yeah, that's a pure substance. It's a beaker of water. There's nothing else in there. It's just water. Water particles are molecules. They're groups of atoms that are chemically joined together. And as long as every molecule is the same, it's still considered a pure substance. Same could be said about like a beaker of salt. If I have a beaker of salt, people will go in the lab and they'll say, oh yeah, that's a pure substance. There's nothing else in there but salt. It looks the same, it's all a bunch of little white salt molecules. But then if they look at the formula, NaCl, that's when they freak out. No, that's not pure, they'll say. You got sodium and chlorine. But if every molecule is sodium chloride, it's still a pure substance. As long as every particle is the same, it's pure. That could mean that your particles are molecules. Mixture is a little different. In a mixture, you have substances that are physically combined. And again, we mentioned physical changes, where you're not changing the structure of each particle. If you're not changing the structure of the particle, then in a mixture, all substances will keep the original properties. And they can be combined in absolutely any ratio, quantity, amount, doesn't matter. So for example, you can make a salad and you can have mostly lettuce and maybe just a few vegetables. Well, I guess lettuce is kind of a vegetable. So maybe you have like mostly lettuce and you throw on like, I don't know, a couple tomatoes and a couple carrots. It's a mixture. It's a physical combination. The lettuce still tastes like lettuce. It's hopefully green, not like wilted or moldy or anything. The carrot still tastes like a carrot, still orange. In the lab, we can make mixtures. We will make mixtures. But everything should keep the same properties. So like I can mix, I can mix iron and water. I could mix iron and water together. The iron will still be magnetic. The water is not. So I could stick a magnet in the water and I can get the iron out. The iron will still keep the same color and texture. It's obviously still solid. The water is still a clear, colorless liquid. I can combine them in any ratios I want. I can sprinkle in just a tiny bit of iron in a giant beaker of water, not sulfur. And it's still a mixture regardless of the quantities. A solution is still a mixture. Let's say you put something like salt in water, and the salt does dissolve. But you can get the salt back with its original properties. All you got to do, evaporate the water. You can evaporate the water and then condense the vapors. Then you've got water in the liquid phase. And what's left in your original container? Crusty, solid salt. You can make a solution of any quantities. You can sprinkle in a little bit of salt. You can sprinkle in a ton of salt. Making a solution is just a mixture. It's a physical change. The two substances can be separated, and you can get them back in the exact same original properties. Okay, so pure, one substance. Mixture has to be two or more. Maybe we'll highlight that too. Two or more substances physically combined. From there, let's break apart our pure substances. Pure substances will either fall under the category of being an element or a compound, which is just what we were kind of mentioning. An element is where you only have one kind of atom. One kind of atom. The example that we used before, our beaker of iron, where we had a beaker and it had only iron atoms. These were all the same. Fe, iron, iron, iron. Iron is an element. If you're ever asked to give an example of an element, you can just look on a periodic table and there's approximately 120 to pick from. The elements are listed on the periodic table. Now, sometimes those elements do exist as single atoms. Most of the time, they exist as single atoms, like iron. There are some elements that are kind of special, and we call them diatomic. Diatomic, meaning two atoms. Oh, brilliant. There are certain elements that like to come in pairs. And again, once we get to like the atomic structure and bonding, there is a reason why hydrogen is more stable if it's two atoms bonded together instead of individual hydrogen atoms. Same with oxygen. A lot of them are gases, actually. Oxygen atoms like to come in pairs. They're more stable that way. And we'll figure out why. So, for example, let's say I have a balloon. Oh, that's a good one. And my balloon is filled with, I don't know, hydrogen. It would look kind of like this. Two hydrogen atoms bonded together. And then I would just have a whole bunch of them. Hydrogen, hydrogen. Hydrogen, hydrogen. And so on. We still say it's an element because there's only one kind of atom. All of the atoms in the balloon are the same. They're all hydrogen. It's okay that there's two of them bonded together. That's fine. As long as my sample only has one kind of atom. The other option is the compound. So when we were looking at this on the last slide, the compound that we used was the water molecule. So here were my water molecules. We'll throw in one more. Little water molecules. Water is H2O. We said this was a pure substance because all particles were the same. They're all H2O molecules. They're all the same. We can be more specific and say that it's a pure substance consisting of a compound. In a compound, you have two or more atoms of different elements chemically combined. Oh, cool. Chemically combined. Remember, we said in a chemical change, you form something with totally new properties. Okay, so individually, hydrogen and oxygen are flammable gases. They bond together as an H2O molecule, and it's used to put out fires. It's a non-flammable liquid. Totally new properties. Same thing with like sodium chloride. If I have a beaker of just sodium chloride, it's a pure substance. Every molecule is the same. They're all sodium chloride molecules. And again, we could say in more detail, it's a pure substance that exists as a compound. It's sodium and chlorine chemically joined together. And as a chemical change, we're going to get new properties. This one will always just like blow my mind. Sodium, we'll look at sodium in the lab. It is a highly reactive metal. Sodium will burst into flames in contact with just water. I would not choose to eat sodium metal. Well, I don't know if I choose to eat any metals, but I certainly wouldn't want to eat sodium, seeing that our bodies are what, like 70% water? Chlorine is a toxic yellow gas. Again, I would not choose to ingest chlorine. But chemically joined together as sodium chloride, we eat it every day. It's totally different than the original elements. I mean, now the sodium chloride compound is like a white crystal. It's not a toxic gas. It's not a flammable metal. Totally new properties. The other thing that we should make note is that a compound needs to have the elements combined in very specific ratios. So for example, in order to make a water molecule, you have to have a 2-to-1 ratio of hydrogen to oxygen. There is no other compound that will have the same properties of water as H2O. 2 hydrogen and 1 oxygen. They must have a very specific ratio. If you change that ratio, you'll change the properties, which again is something that we can do, and we will look at later in the next chapter. So it's a little different than a mixture. A mixture would be a physical combination. A compound is a chemical combination. In a mixture, you could just have any ratio you want, but in a compound, the elements have to be present in a very specific ratio. Okay, so here are our 2 options for pure substances. And it was exactly what we kind of mentioned earlier, that a pure substance could either be a single atom, now we're going to call that an element, or it could be a molecule, and more specifically, maybe compounds, where you have different elements chemically joined together.